So, B0 of t is a probability that time t I take the value 0. So that's something closing. And B1 of t is 1 minus that because of the probability. So basically this is I could just take B0 of t as my one-dimensional process, but it's living at an interval, continuous interval. And it's driven by this really trivial process. A Markov chain that takes a value 0 or 1. So there's not a lot of richness or noise. At each stage, B0 of t can take on maybe just one of a few values. And that's why it's a hard graph. Unlike an LQG problem, where at each time you have a density. There's no way this will ever have a density. It just won't happen. So that's why it's still a frontier. If you want beautiful resources on this, up to date, Raymond van Handel is God. So a lot of this field was a complete desert until a few years ago when this guy who was a physics major decided to dabble in probability theory and just completely resolved all these open problems in the theory of nonlinear flow. It had no probability background at all. And he just knocked out one result after another in this field. And he's going to be visiting in the spring, by the way. He'll be giving I'm organizing a workshop in February. He'll be giving a tutorial on this topic. So, if you're interested, let me know. I'll put you on the mailing list. But see his website. He's one of the few people who cares about teaching. He's got all these beautiful tutorials, mainly in continuous time, so I'm not going to be covering it, but see his website. And sometimes I regret that. I mean, in a way, this would be much prettier if I did it in continuous time, but then the other difficulties. You have to teach your upper-Hamian stochastic calculus. I don't think you want that. Okay. All right, so what do I want to torture you with? Let's see, just a few comments about this. So I told you it's a fully observed Markov chain. So suppose somebody gave me a Markov policy. Well, actually, before I say that, let's consider finite horizon optimal control. So if we were going to try to generalize what we've done before, here's what we'd actually do. There'd be a cost to go. Now, that's given. Sorry. So if we were just going to go and try to generalize what we've done before, the natural sort of family of cost to go functions, look at this stuff. We'd like to know that for any, it's the whole joke about Cambodia. I know nobody here from Cambodia as far as I know. But I mean, the fact is that if I've gone for 10 seconds, what's the best route? Well, I can, basically attribute that, take this as my new initial condition and optimize. And in this case, I want to look at all these possible midway points and capital N is a fixed endpoint. Before we have this as a function of the state, well, of course it's going to be right there. It's actually, it's a function of I of t, but actually it's only of b of t. And this is just some not fixed function of the blue state, but what? It should be the remaining time to go. So this is what we would have gotten in the fully observed case.
Yeah.
You know, we have this family of value functions that we got through dynamic programming, the value iteration algorithm. And this thing that we're looking at here would be a function of the current, oh, it's an n here, I'm sorry, n. It would be a function of the current state. Now, it should be a function of the whole state, but it turns out this disappears. So just a function of the okay. So for some family of functions in belief state. Now, these are functions on this, like, even for a two-state Markov chain, they're functions on a whole interval. So you start off with a two-state Markov chain, you end up having to construct functions on a whole interval. So the complexity is huge. But at least you know there's this beautiful structure. So that's a fact. And so that's sort of fact one. So the belief state evolves on the space of possible probability measures. You know, so this is called the simplex. You know, meaning that defines a probability measure on x. Okay? So if x is equal to 1 up to d, then this simplex. Let's just give it a name. Let's call it S. S is equal to the set of all p in R d plus, such that the summation over I of pi equals 1. That's the definition of the simplex. Okay? So it's at least they're functions of something in Rn, Rd. And it turns out they're concave. And the proof of that's really pretty and trivial and worth doing. And I won't have time to do both. I can't believe how naive I am. I actually thought that I was going to tell you about this and also give you the dynamics of the belief state, but I don't know. Well, why? First, just consider, we know that when we do this, if you believe me this is going to be a controlled Markov chain, let's think of just a linear, Markov policy. I can actually do that. Hold on. Yeah. I'm not even sure I need Markov, but just any admissible policy that only depends on the past. Let's just look at a fixed policy. Instead of, I've got a minimum here over all phi in a way, is really what's happening. Let me just look at a particular t. this is actually a linear function. And why is that? Well, let's just work it out. We can just work it out. Let's see, do I even want to look at it? And that's too many things to say. I'm going to leave it out. We could, that's the thing, I just realized there's too many things to say. So anyway, for each fixed Markov policy, we get something that's linear in B of n. And just intuitively, it's because of the fact that we're, trying to get estimates of x at time n. I only need to know the conditional distribution time. I just have to leave that out. So it's basically by smoothing. So I could spend 20 minutes just on this. But basically, if I want a conditional expectation of anything given the observations up to time n, that's the same as the conditional expectation given the observations up to time n, and actually if I knew xn by some magic, and then given yn. And this is how you convert this into a function of belief. Because this will be a function of xn. Remember this and look to it there. And so so the answer why, so if you believe this statement, that this, the expectation of this given yn is a linear function of belief state for each t, well, the minimum of linear functions is going And that suggests there should be some beautiful algorithms that someday somebody will come up with to approximate concave functions. All right, so that's just one fact. And the fact that this only depends on B of n and not two of them is how we get this property. That's really, that's the main thing. So basically we can, even though not all the assumptions are satisfied, this is not a finite state space MDP, it doesn't satisfy the irreducibility requirement. We still, under general conditions, can expect that these average cost optimality conditions will still hold. If you want to find this, you can use value durations. You can approximate it using value duration. You can use all the tools in the class. You just have to somehow deal with the fact that we've just made the size of the state space enormous. We've gone from, say, 2 states to an entire continuum of states. So this, believe it or not, this is the pretty part. Now these are the egrets flying over Lake Alice. Okay. Any questions? I'm sorry that I just don't feel we have the time to go through this. I just don't think it's worth it. But I do think you have to know what the belief state is. So I'm claiming this is a Markov, chain, controlled Markov chain. I better convince you of that. And given the fact that I can't find one decent reference, I've made you notes. Let me go through and explain this. So the main step really is just to recall one thing, that xy itself can be modeled as an MDP. There's a transition law, the probability given mu of going from a pair x0 to a pair x1, y1. What is it? Well, I think I wrote this down last time, but I'll just write it down again. So this is an exercise for you. First of all, what does this mean? This strange notation here, which I despise, and I'm not going to get rid of it as fast as I can. It's just the probability of jumping to this pair, given you the previous pair, applied here. Same notation we used before. But if you actually look at our dynamics, remember that y is just a function of the previous state. The previous state, I think, in noise. X is just a function of the previous state, u and noise. And the noise was independent. I'll write it down. This is an exercise. So it's the probability that x of t plus 1 equals x1. And the probability that y equals y1. I had independence of the noise driving the state equations and the noise driving the observation equations. These were independent. And so I get a product of probability. So you just have to look at the dynamics. This is an exercise for you. Okay? And all I'm pointing out is, again, that there is that this is a state process for an MDP. I hate this notation, so let's use different notation. Let's write this as new notation. So what would it be? It's supposed to be a lowercase. Because this is so cumbersome, and there's a lack of symmetry between the sub u and this, well, they should be symmetric. This is useful in making the transition from Markov chains to control Markov chains. But now that we're talking about estimation, this notation sucks. And so instead I'm going to use this. All right? All right. So I'm going to start off. So I want. So remember here also notation. It's much more convenient for me to write these a probability like this. Yeah?
Does the conditioning on y0 really do anything for us based on that equation? Right?
Oh yeah, it doesn't. It doesn't. But I'm still going to. I need it. You're absolutely right. It's independent of y0. But I need it anyway, so you're about to see. It's just I need this notation. I'm about to apply Bayes' rule. To get this conditional probability, I need Bayes' rule. And pretending this depends on y0 is this way. absolutely. Thanks for pointing that out. All right. So, yeah.
On the second line, should that be G of X1 WT for the observation model?
Where?
On the line, yeah. The argument.
Instead of X naught.
Yeah.
For
the
Yes. Thank you. Whoa. So you did your homework, thank you. That's right, I mean, yeah. Thank you. All right. So anyway, so there's this guy here, and what I'm going to do is somehow try to keep this. And so this is the thing I really care about, but it's convenient to look at a harder problem first.
Is that a beta n?
Yes. I'm going to write this down and then explain it. Yes, when L is late. And sometimes it's pretty, and right now it smells. So anyway, what I'm doing here is I'm saying it's here is at time n, and I'm conditioned on yn, but I'm writing all this crap out because I just want to specify that at time n, I'm pointing out what the important things I'm observing. That's all I'm doing. So this whole thing is just saying condition on yn. But I emphasize that up to time n, I saw a particular value of y0, particular value of yn, particular value of u0, up to un minus 1. That's the only data I really care about, it turns out. Actually, that was the definition of yn. These guys here, I want to emphasize that I've seen them, because I need them to inform me of the problem.
So yn is one state, right?
What? No, it's an output. It's a measurement. So y is the measurements. And up to time n, I've observed all the outputs up to time n. 0 up to time n. I've computed the inputs based on the observations. And so, therefore, I've seen them. I've seen u of 0 up to u of n. And minus 1 is all I can do. And so that little beta is saying that I'm looking at something much more complicated. I'm looking at the probabilities in the whole sequence, given everything. It's convenient to look at that first. Right? Now this is by Bayes' rule. Now, I've slipped in some new notation here. This is really cumbersome to write down. So when I write x of 0 to n, I mean the whole, sequence, the stochastic process x of 0 to n. And this is the particular value I'm asking, what's the probability of seeing that sequence. So that's the stochastic process, the whole process from 0 to n. That's a particular sequence of numbers. I'm asking what's the probability of it. And the same thing here. So that equality, I'm just writing more compactly in this way. So the probability of A given B is the probability of A and B divided by the probability of B. That's Bayes' rule. The definition of conditional probability.
It's just that top line that's confusing me. We have two separate things written up there?
Yeah.
Yeah, okay.
So this is the thing I really care about. This is the belief state. And first I'm looking at something more complicated. Hardly it's easy to write it down. Okay? There it is. There's the answer. Now, remember, I'm looking for a function of x. And I know it's a probability distribution. Right? This denominator doesn't depend on x, so who cares? You know? If I could compute the top, I'd be done, because I could renormalize it to make it a probability measure. Anything that doesn't depend on x, throw it away. So I'm just going to write this as some constant times. I'm going to put a bullet here for the unnormalized thing, the thing on the top. So if I knew this, I could renormalize it to make it a probability. That's one of the big steps in all this, is to throw away any constants. Now that's not a constant, it depends on observations, but it doesn't depend on x. So if somebody took this away from me, I just renormalize. To make sure this is a probability measure on the sequencing. All right. Well, then we're done because we've got this. You see, the probability of a whole bunch of things happening. You know, now I'm looking at the probability of a sequence of u's, a sequence of x's, a sequence of y's. Well, take a look. It's just going to be a product of these guys. You know, it's a probability of where I started. Of course, the probability of going from there to the next sequence, there to the next sequence. It's just a product. So it's beta. It's whatever the probability of the first guy is. Well, they're given, sorry. Whatever the probability of the first state is. There's some initial distribution on x of 0. And then the probability of going from these guys to this guy. Okay, so I started somewhere. I had a pair x0, y0, u0. What's the probability of going to x1 and y1? You know, it's not going to affect the probability of u. So by nailing everything down, we just get a product formula for this unnormalized conditional probability measure. And this is just the Markov property. I have a controlled Markov chain, and somebody's told me the sequence of inputs. I know that I have this Markov property. All right, so that's the assumption of an MDP model, and I claim that x and y and u form an MDP model. Now that you see, there's our recursive formula if it's a product. You know, so use the prior distribution. Somebody gave me a prior on the initial distribution. We see here that this is just equal to beta n minus 1 bullet of x0 to n minus 1. times this term. This term. There we have it, and I guess you can't see that, but all right. But anyway, if you've got a big product like this, the n minus 1 terms are obviously beta minus 1. And there you have it. It creates the formula. We solved a nonlinear filtering problem. Because at each stage I can then normalize this, and I get the beta that I wanted, although what I really wanted is this. So can somebody tell me now what I have to do to get this? If I've solved the harder problem, can I solve this problem? You know, if somebody told you this, could you find it?
You just have to condition on the previous state.
Not condition. Not condition.
By the probability observation.
What's that?
By the probability observation.
Let me see. Not divide. Not condition, not divide. See, I've got now a probability distribution on all sequences, but I only care about the last value. So it's not divide, not condition, but it starts with an S, sum. So this Bn of x, xn, is a sum over all x0 prime dot 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 all xn minus 1 prime of this beta term. Yeah. If I'm interested in only the last element, I'll sum over all possible values of the previous one. Are you happy with that before going on? You're happy with that.
What were the primes?
What's that?
What were the primes designated?
Oh, yes, you're right. Thank you. That's why I was waiting for you to find my, that was a test. Thank you. I'm just thinking ahead on how I look at that clock and think, yeah, I'd love to just be able to make you feel satisfied that this is over. So anyway, you're all happy with that. I've got, if beta n, this is the probability of the sequence. I sum for all of the first n minus 1 possibilities. I get the probability of the last one. Okay. Now, this is equal to some constant. Do I have one of a can? I'll call it a Cn. Maybe a bullet there. I've already told you that. Now, Cn is a function of everything else. You know, Cn is some C of y0 up to n and u0 up to n minus 1. It's a function of all my observations, but it doesn't depend on x. That's why I can throw it away in a way when I think of this. And then you go sit down and look at this formula and you think, ooh, I've got a recursive formula. Because when I sum all of this over all possible x primes, what do I get? Well, this thing's going to be important, but that's fixed. There'll be a prime there I have to go. So I'll just plug in this formula, and I'll add a prime just right there. And then I have this horrible mess. Yeah, but it's that's side B. Okay. But then let's think about this. I mean, this is my belief state at time n minus 1. With a little bit of algebra that I really don't want to do, I can claim this is equal to the summation over just all x n minus 1 prime. Just rewriting what I have. By taking this term and summing over the first x0 prime, x1 prime, x2 prime, all the way up to x n minus 2 prime, what I get is exactly my unnormalized belief state. And so that's why I have to divide by c n minus 1, and I'll get voila. So all I've done is I've summed over the first n minus 2 elements. First, this is a sum over n minus 1. Well, actually n elements because I'm moving to it. I've only summed over the first n minus 1. When I do that, I get the previous belief state, given my number. My convention right there. Except it's unnormalized, so that's why I took out the c n minus 1. Wait till you've got the new notes. When I sum this over the first, all but the last entry, I get exactly that, but unnormalized. So I had to put a normalizing constant there. And so there you have the filter. I mean, you might not see it this way in books, but can I kill this? What you'd see in a book is you'd see this whole thing called KM, maybe. Or you wouldn't see it at all. You'd see them divide and define KM right away. And I just don't want to do it. It's a waste of ink. But I guess I have to, the way you're all looking at me. Is this going to work better? there was a prime missing here, everyone. Come on. This was over all primes. This is just maybe one error. I'll put this in. No, I need it. I need it. So the nonlinear filters, you might see it in a book, is you look at first of all the unnormalized dynamics. Forget these constants, just the whole thing. And then you would renormalize. So that's the nonlinear filter. And I guess I'm going to force you all to code this once to zero. You know, and basically, I'm not going to give you much more homework, maybe just one more assignment. But you all have to suffer through the nonlinear filter. Because I mean, this, I don't even know what the point is sometimes. I've never felt satisfied giving this lecture. I've given it a million times. And maybe I shouldn't. Maybe this should be an exercise we have to read it and code it. I don't know. But you just have to know Bayes' rule. That's all. And yeah, there's just no way to sit through it. I mean, Bayes' rule, I'll wait. I congratulate you all. But this is, I'll never give a lecture like this in this class. I promise. This was the worst, right? And it's just, you know, all these primes and. But it's okay. So anyway, so I do want you to see this work. So I'll give an exercise where I'll take a linear system and quantize it like that, like this simple first term problem on the left side, and just try Bayes' rule, at least at mass. And then we'll try the common filter, which we'll develop next lecture. So this is ugly. The linear system. That's when you see the egrets again. What I mean by when I say egrets, I mean beauty, the beautiful white birds flying over. But it'll be a fun thing to do. I've never tried it. But take a linear system, quantize it, and apply this filter, and it'll work. And then try the common filter as well. That's what I'm trying to dream that up so it won't kill you in terms of computation. But you definitely need to know this. So that's all for now. So next lecture or two will be on filtering the linear case, and then we'll slowly move into reinforcement. Have a good weekend.